Hello and welcome to my video for Lab 3 for Physics 2212. So in this lab, we are going to be observing and analyzing a changing magnetic field, and then our goals is to set up and perform and analyze an experiment that observes the magnetic field created by a bar magnet. And then we're also going to be creating a computational model that visualizes the magnetic field around a similar bar magnet. So a brief overview of the results, we found that the magnitude of the magnetic dipole moment was around 3.1 joules per Tesla. The average distance was around 0.174 meters, and then the average magnetic field was around 1.8 times 10 to the negative 4 Tesla. So some fundamental concepts and principles that we're using, the main one is the Biot-Savart law, which we've rearranged just a little bit from their normal to give us this equation. Our main use for this is going to be a bit later on, as we have to calculate the magnetic field in our computational model. In our experiment, we are calculating the magnetic field around a bar magnet, which is the value k, which is a combination of constants, times r, the distance, times an unknown value n that we're going to be solving for later on in the experiment. And then in our data analysis that we'll be talking about later, we are plotting this in an xy Cartesian coordinate system. So for the experiment, our system was the magnetic sensor in the phone. Our surroundings were the Earth and the bar magnet. And then initially the phone was held vertically on North's magnetic north and south axis with a meter stick perpendicular to the phone to account for the east-west axis. So it kind of looked like this. Cool. And then for the on-axis experiment, the magnet was moved until the sensor reported a magnetic field of roughly 20 mu Tesla. The resulting distance and magnetic field value were recorded, and this was repeated twice more for a total of 3 data points. Steps 1 and 1a were repeated for the field values of 70, 120, 170, and 220. And values are recorded throughout. Each of these values were then put into a document and averaged together for the data point. And then for off-axis, the magnet was manipulated until the net magnetic field returned roughly 100 mu Tesla. This distance along with the y component were recorded. The phone was moved, so we had the north-south axis like this. We moved the phone at a distance of equal magnitude in a direction perpendicular to this axis created by the first yardstick. And then the x, y, and z components were recorded, and the y component was corrected to account for magnetic field. This procedure was repeated twice more, and the data points were also recorded and averaged. And so here you can see the on-axis part of the experiment. You can also see it over here. And then you can also see us plotting this, like we were talking about plotting ln, the natural log of B of the magnetic field versus the natural log of the position. And then you can see the off-axis experiment data over here. And so we can take and manipulate ln of k, which is the y-intercept of this equation, and we can manipulate the experiment a little bit into this equation and return that 3.1 value that we talked about earlier. Our distance average we found right down here, as well as our magnetic field average, which is right here. For our computational model, we first created some constants. We created mu naught over 4 pi, as well as a cylinder that would simulate or represent the magnet. We created the magnetic field in this function right here using this equation, and then we scaled the arrows to allow us to better visualize them in the model. And then over here we create each of the unique vectors that we'll be analyzing, as well as the off-axis experiment we discussed earlier. And here you can see each of the arrows are visualized. This is the bar magnet right here, and then here are the distinct values for each of the axes for each of the vectors that we created. And so to discuss a little bit of error, some random error that could have happened was the fluctuation in the magnetic field. So while we didn't perform this experiment outside, we were not able to eliminate all potential interference of any kind of like electronics or other, maybe there was like a really big magnet in the ground, I have no idea, but it's possible that certain interferences like this cause fluctuations in the data points themselves. And then a systematic error that would have caused the entire data set to be shifted was a rounding error on the app. So the app could only report values up to a certain number of significant figures, and so this could cause minor fluctuations in the values of all data points. And so what if we hadn't oriented our experiment to compensate for magnetic north and instead laid out our meter stick at some intermediate angle? And so if we did not, then we would have true magnetic north pointing this way, and then we would have this pointing this way, and then we would have to separate our values into components based off of this unknown angle theta. Sort of complicated calculation, so it's really good that we accounted for this. And then what if we were to stick two identical magnets together end to end and run the experiment again? And so we've got one bar magnet right here, and then we're just going to slap one right on top. So let's just do south, north, south, north. And so we have one bar magnet which has a field like this, and then we have this other bar magnet, and because this is all in the same direction, every vector for the magnetic field would be multiplied by a value of 2, and so the magnitude of this would be would increase by a factor of roughly 2. All right, thank you guys so much.